What we see around 3i Atlas is an abundance of deuterium at a level that is 1,000 times larger than the average cosmic value. We have never seen that in comets or asteroids within the solar system. It's much larger than that.
After months of observation and analysis, new data has revealed something deeply unusual about 3i Atlas. It is something that does not easily fit within the boundaries of established astrophysics. Hidden within the signals surrounding this object is a discovery that has immediately raised eyebrows across the scientific community, a chemical signature tied to what many are calling nuclear fuel. The presence of this material, in quantities far beyond what should naturally exist, has transformed 3i Atlas from just another interstellar visitor into a genuine scientific mystery. Because if the data is correct, then this object is carrying something we have never seen before in anything like it. An anomaly so extreme that it forces scientists to question not just where it came from, but whether our current understanding of how such objects form is missing something important. Deuterium, sometimes referred to as heavy hydrogen, is not an exotic substance in itself. It exists naturally throughout the universe, formed in the earliest moments after the Big Bang, and later incorporated into stars, planets, and interstellar clouds. What makes it special is its role in nuclear fusion. Unlike ordinary hydrogen, deuterium contains an additional neutron alongside its proton, making it particularly useful in reactions that release enormous amounts of energy. For decades, scientists have studied deuterium as a potential fuel source for controlled fusion, a process that could one day provide nearly limitless clean energy. But while deuterium is common, it typically appears in very small, predictable ratios compared to regular hydrogen. That is precisely why the measurements surrounding 3i Atlas are so difficult to reconcile. According to the observations discussed by Avi Loeb, the deuterium levels associated with this object appear to be roughly 1,000 times higher than the average cosmic abundance. This is not a minor anomaly. It is a deviation so large that it challenges the assumptions scientists rely on when interpreting the chemical makeup of celestial bodies. In familiar environments, such as comets within our own solar system, deuterium levels remain within a relatively narrow range. Even when variations occur, they do so gradually, shaped by temperature, radiation exposure, and the history of the object's formation. But nothing in the existing record prepares us for a spike of this magnitude. The first instinct in science is not to leap to extraordinary conclusions, but to test whether the observation itself can be explained through known mechanisms. One possibility is that 3i Atlas formed in an exceptionally cold region of space, where chemical processes might favor the enrichment of deuterium. In theory, extremely low temperatures can alter how molecules form and bond, leading to localized concentrations of certain isotopes. Yet even this explanation struggles under scrutiny. The early universe, while initially hot, cooled over time, and the environments in which stars and planetary systems formed were not uniformly cold enough to produce such extreme deviations. Moreover, the distribution of matter in those early systems would not easily support the creation of a large population of objects with such unusual compositions, let alone one that we happen to detect passing through our solar system. The scale of 3i Atlas only deepens the mystery. Described as being roughly the size of a city, it is not a small fragment or a piece of debris. It is a substantial body, one that implies a long and complex formation history. Objects of this size do not simply emerge from random fluctuations. They are the result of sustained processes, accretion, collision, and gradual growth over time. If the deuterium measurements are accurate, then whatever environment produced this object must have been capable of maintaining highly unusual conditions across a significant region of space. That alone would make it an outlier in our understanding of cosmic evolution. Then there are the jets. Observations indicate that 3i Atlas is emitting 3 distinct jets of material, oriented in a configuration that does not align neatly with standard models of cometary activity. In typical comets, jets form when solar radiation heats the surface, causing volatile materials like ice to sublimate and escape into space. These jets are usually uneven, driven by the rotation of the object and the distribution of its material composition. But the reported configuration here appears more structured, more stable, and more difficult to attribute to random surface processes. The geometry alone raises questions about what lies beneath the surface and how it interacts with its environment. Individually, each of these anomalies might be explainable, Science has a long history of encountering strange observations that eventually find their place within a broader framework. But taken together, the elevated deuterium levels, the size of the object, the unusual jet configuration, they form a pattern that resists easy classification. It is this accumulation of discrepancies that has led some researchers, including Loeb, to describe 3I Atlas as a deeply puzzling object, one that may be pointing toward gaps in our current models. To understand the significance of such a situation, it helps to look back at moments in history when scientific understanding was pushed to its limits. During the Manhattan Project, for example, researchers confronted the unknown in a very different context. At one point, there was a genuine concern that detonating a nuclear device might trigger a runaway reaction in Earth's atmosphere. The fear, though ultimately unfounded, was rooted in incomplete knowledge. Careful calculations later showed that the conditions required for such a reaction simply could not be met. The lesson was not that the fear was foolish, but that uncertainty is an inherent part of exploring new territory. In the case of 3I Atlas, the uncertainty lies not in potential danger, but in interpretation. When confronted with data that does not fit, scientists must decide whether to expand existing theories or consider entirely new possibilities. The most conservative approach is to assume that the anomaly will eventually be explained through natural processes that we have not yet fully understood. This has been the outcome in the vast majority of cases throughout scientific history. However, the more anomalies that accumulate, the more pressure there is to revisit foundational assumptions. It is in this space of uncertainty that more speculative ideas begin to surface. Loeb, known for his willingness to explore unconventional interpretations, has suggested that the unusual properties of objects like 3I Atlas could, in principle, be consistent with artificial origins. This does not mean that the object is definitively engineered, nor does it serve as evidence of extraterrestrial technology. Rather, it represents an attempt to keep the range of possibilities open when the data resists straightforward explanation. Such suggestions are often met with skepticism, and rightly so, because extraordinary claims require extraordinary evidence. At present, that level of evidence does not exist. What does exist is a rare observational opportunity, one that, in some ways, has already passed. 3I Atlas traveled along a trajectory that kept it within view for an extended period, roughly a year, allowing astronomers to collect more data than is typical for interstellar visitors. Its path near the plane of the planets made it particularly accessible to observation, giving researchers time to study its behavior, composition, and evolution. And yet, despite this advantage, humanity did not have the capability or readiness to send a mission to intercept it. This limitation underscores a broader challenge in modern astronomy. Interstellar objects are, by their nature, transient. They appear without warning, move quickly through the solar system, and then disappear into the depths of space. Detecting them early enough to plan and execute a mission requires a level of preparedness that we are only beginning to develop. The passage of 3I Atlas serves as both a scientific opportunity and a reminder of what we currently lack: the ability to respond in real time to rare events that could reshape our understanding of the universe. Looking ahead, there's a growing recognition that future detections must be handled differently. Improved surveys, more sensitive instruments, and faster response systems could make it possible to identify interstellar objects sooner and track them more precisely. With enough warning, a dedicated mission could be launched to approach, study, and perhaps even sample such an object directly. The data obtained from such an encounter would be invaluable, providing clarity where remote observations leave room for ambiguity. Beyond the immediate scientific questions, the discussion surrounding 3I Atlas also touches on a broader cultural and institutional context. References to government interest in unidentified phenomena, as well as the development of new platforms for sharing information, reflect a growing awareness that not all observations can be easily categorized. Advances in sensor technology have made it possible to detect objects and events that would have gone unnoticed just a decade ago. As a result, the boundary between the known and the unknown is constantly shifting. In this evolving landscape, collaboration becomes essential. The complexity of the questions raised by objects like 3I Atlas requires input from multiple disciplines: astronomy, physics, chemistry, and beyond. It also calls for a balance between skepticism and openness, between the rigorous testing of hypotheses and the willingness to consider new ideas. The goal is not to jump to conclusions, but to ensure that no possibility is dismissed prematurely. Ultimately, the story of 3i Atlas is not about definitive answers, but about the process of inquiry itself. It is a reminder that even in an age of advanced technology and detailed models, the universe retains its capacity to surprise us. Each anomaly, each unexpected measurement, is an invitation to look deeper, to question assumptions, and to refine our understanding. Whether the deuterium levels turn out to be the result of an unknown natural process or something more unusual, the journey toward that answer will expand the boundaries of human knowledge, and perhaps that is the most important outcome. Objects like 3i Atlas do more than challenge scientific models. They shift perspective. They highlight the vastness of the cosmos and the limits of our current understanding, while also pointing toward the possibilities that lie ahead. The next interstellar visitor may arrive at any time, carrying with it new data, new mysteries, and new opportunities. When it does, the lessons learned from this encounter will shape how we respond. Until then, 3i Atlas remains what it has been from the moment it was first detected, a messenger from beyond our solar system, bearing clues that we are only beginning to decipher.